Okay, so now let's solve this example for calculating the hydrostatic pressure force on the curved surface. So again, I just want to remind you what we were trying to do. So we have a channel, a water channel, which is this circle, and then it is filled up to half of it is filled with some water, and we wanted to calculate the the force that is exerted on this side of the channel, right? This BC section of the channel. Okay, so this is what we are trying to do. Okay, and to do that, the first thing I wanna do is I want to draw the free body diagram of this. Okay, so I've already drawn it here. So this is what you can see. This is the free body diagram of that. Okay, so we have this section here, A, B, C from front view. Okay, and so the forces that we have are as follows. The first one is the weight of the water. So this is the weight of the water, and it goes through the center of the gravity. So the center of the gravity of this section, and we have this weight of water here that is shown here. On the other hand, we have this, let me for now clean this. I will come back to this again. And the other hand, we also have the hydrostatic pressure that is exerted by the water from this side to the fluid, to this section, right? So as you see, if I want to calculate the force that is exerted on this plane here, let me show it on this plane. Okay, let me kind of zoom here. On this plane, the force that is exerted is this hydrostatic force, right? Because we have this force, that is these small elements that are exerted on this. Okay, and so the total force, we are going to show it with F1. Okay, the total force that is exerted on this is shown with this F1. That accounts for all these hydrostatic pressure forces on this vertical plane, right? We have a vertical plane here, okay? And then, so these are the forces that are exerted to this section, ABC, by the fluid, okay? And so because the fluid here is at rest, so this means that the sigma of the forces, the total forces, should be 0, right? Because we don't have acceleration. A is 0, so the sigma of the forces should be 0. And so for completing this body diagram, we need the BC section, the conduit wall should also exert some forces on the fluid as well, right? It tolerates the weight of this water on top of that, so we have to have a vertical force. So it has exerts a vertical force on this fluid, which I show it as F vertical. And also, it should exert a horizontal force to this fluid as well, because we have this F1 here, this hydrostatic pressure force here, that is exerted on this fluid. So, therefore, it has to exert this F horizontal as well. So, this is how I draw the free body diagram because it's easier, but you can imagine the real, if you just want to draw it for this element, the free body diagram is gonna look like something like this, right? So it's gonna be, here we have pressure by the water here, which is gonna be rho g h, where h is 3 meter. And then here we have a 0 because it's the surface, so we are gonna have something like this, right, where the pressure force is always perpendicular to the surface, right? And if you want to calculate this is going to be very difficult. And you see that, so the sum of all the horizontal forces is going to be this, and then sum of the vertical forces is going to be this vertical force. And so because this is so difficult, I'm just going to consider a simpler version of that, which is shown here. So if you consider this, then you can simply draw a free body diagram where you can simply calculate it for these curved surfaces. So this is something you need to know, and this is a technique that we use for kind of analyzing these free body diagrams in curved surfaces. And this is a 3D view of that. So in a 3D, I just plotted it. So we have the 3 meter and 3 meter here. So this is going to be, let me show it. This will be A, B, C here. We have A, B, C. And then this is in 2 meters, right? So this has gone 2 meters, right? And so this is the free body diagram. So F1 is exerted on this plane, on this green plane that you see here. And the F1 is the total, the sum of all these hydrostatic forces, right, that are exerted on this plane. Okay. And then we have the weight of water that we have to calculate. And so these would be the forces that are exerted by the fluid to this channel. Okay, so let me get started. So the first thing I want to do is to calculate the magnitude of this force. So for calculating the magnitude of F1, it is equal to rho g hc, which is going to give me the pressure, the average pressure, times A, which is the area that this force is acting on. And the area is going to be what? Is going to be this green area here, right? Because this is the area which this force is acting on. These pressure forces are acting on, okay? So I need to know the HC. The HC is the first moment of area. So you can either use these formulas here that we learned. So for example, for let's see, let me see if I can find it. So HC is here, right? This is the first moment of area. It's gonna be the center, right? The center of that, the center of the area of that, okay? So in this case, it's gonna be 1/2, right? So let me show it. This is because this is the first area moment, so it's gonna be the center of this area that we have, which is gonna be 1/2 of it, okay? So let me show it. So it will be 10, the density of water is 10 to the 3 times G, which is 9.81 Newton per meter cube. And then the HC is gonna be 3 meters, 3 meters where we have that, over 2. This is going to be the HC. Okay? And the area is going to be 3 meter times 2 meters, right? This is the rectangle we have here. Okay. So this is going to give me 88.3 kilonewton. Okay. So $88.3 kilonewton. So let me explain. So the HC here. So the HC is for this problem is gonna be 3 meter over 2, right? And this is one way of solving it by HC, and I want to give you another way if it is hard for you to calculate HC based on these, but it should be easy based on those tables, but which is it should be the center of the area. But another way to solve it is as follows. So, and this is how I also calculate sometimes myself, is I say, okay, I have this much force, and the bottom of it, the highest one is gonna be this one, is rho g times 3 meters, right? And here I have 0. So I have a rectangle which I know, so its sides, and I want to calculate the area of that, right? To get the total forces. So here I have rho g3. Okay, so I know this side, and then I also know this side, which is 3 meters. Okay, and I want to calculate the area of this. To get the magnitude of the force, right? So it's easy, the area of that. What is the area of this? Is gonna be 1/2 of this side, rho g3, times this one, 3, okay, and then I want to multiply it by this. This is the total force on one on this side, and just and then I have to multiply it by this 2 meter to get the total force, right? So to get the total force on all this section, right? And if you see that, so let me show it maybe another way here. So we have this. You want to calculate the volume of this this thing, something like this. Let me show from another side so you better understand it. So we have this triangle. These are all 90 degrees. So you have 3 meter here, and then you have rho g3 here, and then you have 2 meters here. So the first thing is you calculate the area of this. area. So the first thing is that you calculate the area of this red area that I've shown, and then you have to multiply it by this length to get the total area of the forces, right? So I first calculated the area of this side, and then I multiplied it by 2 to get the total area. Okay, so that is what I did. The total volume of the forces, this is going to be the total forces that are acting on this plane, this green plane that I have shown here. Okay, so this is another way of solving that if you don't want to use the other classic method. And if you see, the results are going to be the same. It's 1/2 rho g3 so let me calculate it. It's going to be 1/2 of 10 to 3 times 981 Newton per meter cube times 3 meters times 2 meter. And if you see, this equals to yeah, I forgot something. So this I have 3 meters here too. So I have 9.81 times 3, and then I have another 3 meters, and then a 2 meters. So if you this is just this one, right? So if you compare these this one with this one here, you see they look similar. So at the end of the day, we have the same thing here, which is 88.3 kilonewton. Okay, so this is another way. So this is typically what I do. I mean, this is a simple geometry problem that you can solve. If you don't want to use those tables, it's just kind of calculating a volume of the force, a volume and all areas to get the total force, okay, the total sum of the forces. Or, I mean, you can use the original way of using that, which was calculating the average pressure through this formula, which is rho GHC, times the area that this pressure is acting on, which is this green area here, 3 meter by 2 meter. And the HC is the center of area, the height of the center of area, which is going to be the center of this area is going to be half of it, right? X here. It's going to be 3/2. And so this is where you can find the magnitude of that, okay? And so let's now look at the location of that. So the location of it, it's gonna be here, because this is a triangle, so this force is gonna act. For the location, we use the second area of moment, right? And so the FR, the resultant force, is gonna act on, because this is a triangle, it's gonna be on 1/3 from the bottom, which is gonna be here 1 meter from this side and 2 meters from top. And this is the resultant force that acts. And this shows the location of this force, right? This is what we know from the triangle. It's going to be 1/3, and we had it in this example and also in previous examples, and also in the tables. We also have that for a rectangle, for a triangle. The location of the force is going to be 1/3 of the from this side. So for example, if you have here a triangle like this and this side is A, the location of the force is going to be 1/3, right? So this is what we know for a triangle. Okay, so I have it here, and then let me now calculate the other thing. So this is, we know, is going to be 1 meter from here. So it's going to be 1 meter from here and 2 meter from top. This is the location of this force. And now let's calculate the second force, which is the weight of the water. Okay, so W, which is weight of water, is going to be what? It's going to be all this volume that we have. So this volume of times the density. So the W is going to be is mg, right? And what is the mass? What is the mass here? The mass, I can just show it as rho, the density of water, times the total volume of that, and then multiplied by g. So V is volume, right? You know, because the density is defined as m over V, right? And so I can write m as rho times V, the volume, the total volume. And so the total volume I have to calculate. So the total volume of this section here, what is going to be the total volume of that? The whole for this, which is, I'm showing it with this purple color. So I want to calculate it. So the total volume of it is going to be, first, the volume of this section, the area of this section, and then I have to calculate that and then multiply it by these 2 meters to get the total volume, okay? So the area of that section is pi over pi 3 square is going to be the area of the whole circle here, and then I'm just interested in 1/4 of that, right? 1/4 of a full circle. So I just need to divide it by 4. So it's going to be the area of this section here. Okay, and then in order to get the volume, I need to, this is meter square, I need a meter cube, so I need to multiply it by these 2 meters here. So this is going to give me meter cube, something in meter cube, right? Which I need to calculate. Okay, so this is the volume. So let me just write it down here. We have, let me copy it. So you better, yeah, so we have it here. So let me, yeah. It's gonna be rho g v, which equals to, what is rho and g and v? So rho of water is 10 to the 3. Then we have 9.81 Newton per meter cube. And then we have the volume, which I have to multiply it. So the volume is gonna be pi 3 square, which I have here, over 4 meter square. And then I have times 2 meters. And this is going to be the total force for the weight of the water, okay, which is gonna be 100, if you calculate, it's gonna be 138.6 kilonewton. Okay, and this acts at the center of gravity, or CG, which for this shape is 4r over 3 pi. So you can go to the tables. I don't think I have mentioned it here. Yeah, so in the tables you can see what is going to be the table, the center of gravity for this shape, okay? So you can find it there. So it's going to be 4r over 3 pi to get the location of this center of gravity. Okay, for these 1/4 of a circle, okay, which is gonna be 1.27 meters to the right of AC. So it acts from here 1.27 meters. Okay, this is what you can calculate again, find it from tables. They have this formula for center of gravity for different shapes. Okay, they have already calculated for you, so we used that from those tables. Okay, so now we have everything. We have F1 and we have W. So we should be able to calculate F vertical and horizontal, okay? So let me just write it down here. So to satisfy equilibrium, we need the sigma of F of all forces should be 0. So in the horizontal direction, in the x direction, if this is x direction, let's say, this is x direction and this is y direction. So in the x direction, this means that FH, horizontal, should equal to F1, right? So FH, which is this one, horizontal, should equal to F1, and F vertical in the y direction should also equal to W. So let me write it down. F1, FH equals to F1. What is F1? F1 is 88.3 kilonewton. And F vertical is equal to W, which is shown here. And so it's gonna be equals to W, which equals to what we had calculated here, which is 138.6 kilonewton. Okay. So I have found these vertical and horizontal forces that the water exerts on this conduit wall. And now let's calculate the total force, the total resultant force. So the total force is going to be something like this. We can calculate it as follows. So we have a horizontal force and a vertical force, right? So I just need to calculate the magnitude of the total force, which is going to be the resultant force on this. So the total force is going to be like this. I can calculate it as if this is the horizontal one, and then this is the vertical force, Fv, and this is Fh. So the resultant force is going to be something like this, right? So Fr can be calculated as a square root of Fh square plus Fv square. Okay, so it's gonna be square root of 88.3 kilonewton square plus 138.6 square, and square root of that is going to be 164.3 kilonewton. So this is the magnitude of the resultant force that is exerted by the fluid to this section BC. Okay, and now let's find the location. So the location of this force, I can find it as follows. I know the geometry, so let me show the geometry. We have this quadrant of a circle. Okay, so here we have the center of gravity, which is here, and this line. Where this is going to be 1.27 meter. We know it from our calculations. And then we also have these, the other horizontal force, which acts at 2 meter from top or 1 meter from bottom. So this is going to be 1 meter. And this is 2 meters. So we have a force that acts in this direction here. And then another one that acts in this direction. Okay, so the total force should act somewhere in between these two. And this is going to be Fr with this angle theta. Okay, so this is Fh, horizontal force, and this is the Fv, vertical force. And the total force should be something like that. So I can calculate I just need to calculate the location of that, so which is going to be the theta. If I just know the theta, then that's where it's going to act. So I know from this shape that the tangent of theta is what? Is going to be this 1.27 over these 2 meters here. Right, so let me show it with another color. So it's going to be this 1.27 meter over these 2 meters. So the theta is the arctangent of 1.27 over 2 meter. Okay, so this force is acted, if I want to show it again, acts along this line here, is perpendicular to the surface FR, and this theta, the theta is the one that we found, right? Which is the arctangent of 1.27 over 2. That's going to be the value of theta. Okay. This theta is just this theta that I've shown here. Okay, so this is how you can approach this kind of problems when you have a curved surface. So what you need to do is you need to find, the first thing you need to do is to draw a free body diagram and try to kind of draw it in a very simple way where you can simply calculate the forces. So don't overcomplicate it. Something like this, this one that we have shown here, would be easy to solve and easy to calculate because we know most of the properties of that. So then you need to calculate the forces, the hydrostatic forces, which is this F1, the magnitude of that, and also the location of that, and then also the weight of water, which is shown here. Okay. So all the forces that act on that. So you just draw the free body diagram, and then we calculated the magnitude of the hydrostatic force through 2 methods. Either you use the HC from the first moment, or you use this method that I showed here, which is just a simple geometry or geometry calculations. And then the location of that force can be found by the second area of moment, which is for this triangle is going to be 1/3 from the bottom of that. And then the weight of the water, which is shown here, you just calculate the volume of the water and then multiply it by rho g. So it's going to give us the weight of the water, which acts at the center of the gravity. And the center of gravity, you can find it from tables for different shapes. For this one is 4r over 3 pi. And then you find the horizontal and vertical forces. Then you square root horizontal and vertical forces to get the total force. And for getting the location, you simply draw them and calculate the angle based on the horizontal and vertical forces that you found, for example, for these curved surfaces. Okay? So it's going to be the arctangent of 1.27 over 2. Okay, so now I want to briefly mention buoyancy and Archimedes principle. It's a simple principle, again, gives you more intuition about some of these forces, buoyancy forces. So you don't necessarily need this to calculate any of hydrostatic forces that we learned or any, but this will give you more insight so a buoyant force is the resultant force fluid force on the body of objects in a fluid. Okay. So let's calculate it. So if we have an object here, any object, let me maybe show it with this, it's easier. So this object is underwater, say up to here, it's water. Let me maybe just put it a little bit down. So we have water up to here. This is the free surface. And so this has H1 from here, and then H2 from here. Okay, so, and it has a weight which acts on the center of it, center of gravity of this shape, which is here. And this is the edge of the object, the height of the object. So now I want to plot the hydrostatic forces that are exerted on this fluid. Okay. So you know, because of symmetry, these two are going to cancel out, right? These are the same. So the horizontal forces are going to cancel out. I don't want to show them, but for the vertical forces on this plate, first I want to calculate on this plate. So on this plate we have these pressure forces. Small pressure forces. With the amount of rho g h1, right? And on the bottom we have a larger force, a little bit larger force, because h2 is larger. So I'm gonna just show it here. On the bottom plate, this is gonna be pressure, which is equal to rho gh2. So the sum of the forces, the total force on this side, I can show it as F1 on top, and then 1 F2 at the bottom. So the buoyancy force is the resultant fluid force on the body of the objects in a fluid. Okay, so it's gonna be the difference between these two forces, F2 minus F1, right? Because this is the force that fluid exerts on this body. It's the resultant, the net force that it kind of exerts on this body that we have. So this is the body, let's say, we are considering. Okay. So F2 minus F1, I can calculate it. It's going to be raw water G times H2 minus H1 times the area that is acting on. Okay. So this F2 is going to be this rho G H2 times area, and this also equals to rho G H1 times area. So this is going to be F2 minus F1. And so I can show that F buoyant equals to raw water G, and instead of H2 minus H1, I can write it as H object, right? Which is what we have here. So I have A times H object, and this equals to raw water G. A times H object is going to be the volume of the object, right? The area times the height of that. So it's going to give me the volume of the object. Okay, so this is an interesting formula. This means that the fluid, how much a fluid exerts a force on any object that is inside that. And the amount of the force is raw water, G water, and the volume of that object. So it doesn't matter what is the density of that object. It can be a very dense or very low density object, but the amount of the force that is exerted on that fluid, on that object, is by the fluid is the volume of the object inside fluid. So the volume of it that is inside the fluid times rho W times G. This is the amount of force, buoyant force, that is kind of exerted by the fluid to that object. So let me show it in another, let me write it down. And this is gives you an insight in any of the objects that you want to calculate the buoyancy force on that, and see how much buoyant force is exerted by the fluid into that object. You can just use this formula that we simply found by writing the hydrostatic pressure forces. Okay, so the Archimedes principle states, and Archimedes was the first one who kind of found this, and you might know the story behind that. Like, he went to kind of take a bath, and then he found this kind of general principle. So the principle states that buoyant force on any object inside the fluid has a magnitude equal to the weight of the fluid displaced by the body and is directed vertically upward. It is directed vertically upward because the horizontal forces are going to cancel out. Okay, so the net force, the net buoyant force is going to be always vertically upward. So let me show you an example. So say we have a tank of water, and then we have an object. Okay. So this object has a volume of V1. Okay. So put this object, if we put the object inside the fluid, what happens? So if you put it inside, we will see that water goes out, right? Some water goes out. Some water is displaced. So this should be right at the here. So some water is displaced, so and goes out. Okay. So, and I want to know what is the buoyant force, the force that this the fluid exerts on this body, on this object. And the amount of that force can be found if we just calculate how much water, if say we have something here that gets this water. So how much water was displaced, you just calculate its weight, the weight of that much water that is displaced and is getting out of that, and that would be the amount of that buoyant force. Okay, so this is what this Archimedes principle states. So F buoyant equals to rho g times V1, rho of water. So it doesn't matter what is the density of the object. So if this has a rho obj, and then the water has rho water, the buoyant force is going to be rho water times g times the volume of the water that is displaced, which I showed here. And if you completely put it inside, it's going to be, it's completely inside the water, it's going to be rho g times the volume of the object. So if it is, for example, if it is not fully inside, say we had this, like half of it was only inside. So this much water was displaced, right? So the buoyant force would be rho water G, and if this has, say, a volume of VD, this is going to be rho water G times VD. This is going to be the amount of displaced water and the amount of buoyant force that is acted on this object, okay? So this is a kind of Archimedes principle that you can see, you can get it based on also the calculating hydrostatic pressure force. So we don't really need to know it, but this is also going to give us some insight that what is really the amount of the net force, the net total force that the fluid exerts on any object inside that, okay? And you can get it again by these writing these hydrostatic pressure force distributions, okay? Okay, so in the next lecture, I think we are going to have only stability and pressure variation in fluid with rigid body motion. And after these two, which is going to probably take half a lecture, we will finish chapter 2. And then after that, we are going to go to chapter 3, which is mostly about fluid dynamics and Bernoulli equation. Thank you very much, everyone.